It's wonderful to be back in Edinburgh after many years not here because of the pandemic, I think. Uh, so yeah, I spent a lot of time here as a grad student visiting Clark and spent many hours in this room specifically even. Uh, and yeah, so this is about a project with this wonderful list of people, including Katrin, who's here. Um, that's but I also want to thank Clark a lot for first setting up so nicely in his talks for me to talk about this, and second also for many ideas that are very important in this work. I mean, somehow it's realizing some dreams we had a long time ago and doing some other things. But yeah, there's a kind of big contribution from Clark in this. And yeah, so let me start with some motivation. Um, which is, say we have X, which is what's called a topologically Noetherian scheme. So this just means that the underlying topological space is a Noetherian space. Um, so for example, a Noetherian scheme, this is just a hypothesis so that everything I say is in the context of what these people did. And you have X bar to X a geometric point. So this is a choice of a point of the underlying space and a separable closure of its residue field. So in their work on the Pro-Étale topology, Bott and Schulze defined a topological group um, that they write as pi1 pro-et x bar, called the Pro-Étale fundamental group. Okay, so where am I supposed to put the board now? Is, no. Maybe it's better to go over here.
Should have looked to me for advice. You saw what my talk was like.
Yes.
Sorry, I also have it written on them actually.
Yeah, these boards are somehow kind of confusing. Okay, anyway, with the following key properties. So the first.
Is this always actually like a small topological group? Sorry, because I always, when I hear Pro-Étale, I worry that like
A small topological group. Yeah. Yeah. So so their interest in defining this was that for a long time in algebraic geometry, people had studied this thing called the Étale fundamental group. It has many nice features, but some deficiencies. So the first thing is that Étale fundamental group, as the type of thing that's been discussed in Clark's talk, is a profinite group. So if you profinitely complete this, this recovers the Étale fundamental. So it recovers a classical invariant. And second, if X is what's called geometrically unibranch, so such an example is if you're smooth over a field, so any kind of reasonable type of scheme, then these two guys actually already agree. But they don't in general. And one reason that they don't is that in general, this Étale fundamental group, it it doesn't classify local systems with coefficients in somewhat complicated topological rings like QL. And this is of interest in arithmetic geometry is trying to understand local systems uh, with coefficients in rings like QL or other topological rings. But the nice thing about this Pro Etal guy is it always this classifies QL local systems. So QL local systems are really representations of this now topological group. And here you should use the topology on the L-adic rationals. And then, well, the fourth one is maybe not a helpful property, but it just normalizes stuff, is that in general, this pi1 pro etal is not the limit of a pro group. So this said that in some nice situations, it's a profinite group, or at least its profinite completion recovers this. But in general, if your scheme is not so nice, then you can't even write it as some inverse limit of groups with a discrete topology, even if you allow for infinite groups.
I have no intuition for this geometrically unibranch, but are there simple examples of varieties for which those two are different already? Pro Etal.
Yeah. So if you identify 2-point curve, then I mean, so the Pro Etal one will recover Z, but the Etal one is, well, it's a profinite group and it's Z hat.
2 points on the curve, like on a P1, you mean?
Yeah,
P1 with two.
yeah, you identify 2 points.
The topological fundamental group of that is also Z.
Yeah, the topological fundamental group. So yeah. So there are some simple examples like this. Okay, but the point that we wanted to try to understand is that people have understood a refinement of the Étale fundamental group called the Étale homotopy type. And we wanted a refinement of this pro-Étale thing. But the problem here is somehow that in the Étale setting, well, this is a profinite group, so you can work with some kind of pro object, so some pro anima. Now, this tells you that there's no way you can possibly do that. And I mean, this is essentially the reason we got involved in condensed mathematics, or the setup of that. And so the desire that you might have is to construct a condensed anima that I call pi infinity cond of x, such that its fundamental group, which is now a condensed group, so that's something like a topological group, it recovers this pi1 pro etal. And let me put this in quotes because we'll have to be a little bit careful about what exactly that means. The spoiler is it won't be exactly that, but it will be some more refined thing that's actually in many ways better. And refining the listed properties. Okay, so that's the type of object we want. And well, since this is a meeting of young homotopy theorists, and I think also the area is not necessarily so well known, I figured I would first try to explain a little bit about how you do the Étale homotopy type, and maybe you can learn something for this. And then well, explain kind of three definitions of this condensed homotopy type and some results we proved. Oh yeah, by the way, this paper you can find on my website and on the archive whenever they accept the thing that I posted last night. So if you feel like looking, you can look there. Yeah.
So what they actually write down in the paper is it the condensed group that then happens to be a topological group?
No. No, they really write down a topological group. And so, yeah. And so that's kind of the part of the source of the difference between the thing that we write down and what they write down. And the other part of the problem is that this specific statement is true, but then it's a little bit hard to identify for exactly what topological rings you can replace this for. And
So this kind of thing with like a topologically nilpotent unit, those rings have a name or something. Is this the kind of rings for which this works?
so I think it should work for any rings, like, so that probably the underlying additive group is a Newhy group. So this is like means it's like determined by the forgetful functor from sets with a continuous action of the group. Yeah. So it's kind of not so well behaved actually. It has some nice features, but some bad features. But maybe I get back to this at some later point. Yeah. Any other questions? So um, so let me tell you about the étale homotopy type of this thing called the pro-étale topology. Because somehow I like this observation about some way you can define it. So yeah, I'll use Clark's notation for the étale topos. And so there's a general way of extracting some kind of homotopy type that's not an anima, but a pro-anima from a topos. And this goes by the name of shape theory. And the reason for this is because it refines something called shape theory that was like developed by originally Borsuk and Ulam, I think, but like has been extensively studied in Poland. But now you can just do this with sheaf theory. So say we have X that's an infinity topos. I'll write gamma lower star for the geometric morphism to anima. Now, this is the terminal object in infinity topoi, so there's a unique one, but I can tell you what it is, which is it sends an object to maps in X from the terminal object to F. So if you were sheaves on something, that's literally global sections, and that's why I call it gamma lower star. And by some generalities on some universal properties, so it has a left adjoint, which I call gamma upper star. So that's some version of the constant sheaf functor. This functor admits called a pro left adjoint. Gamma lower sharp. So this goes from pro of anima to oh, sorry, wrong direction, from X to pro of anima. So yeah, this type of functor in general won't have a left adjoint, but as long as you're willing to enlarge the target to pro objects, so things that are formal co-filtered diagrams of anima, then it does admit a left adjoint. And the maybe kind of abstract definition of what this kind of homotopy type of a topos is the following. So you have this pro-left adjoint. It turns out it doesn't really have any properties. It doesn't need to preserve finite products. It doesn't need to preserve finite limits. It doesn't need to preserve the terminal object. And this is what this makes this definition reasonable, is that the shape of x is often written pi infinity of x. Well, I have this random functor that's just given to me via universal properties, and I can apply it to the terminal object. And okay, I mean, why does this need to be well behaved? Well, let me give you, I'll say one, give you an example, which is, so the first thing is to say, yeah, I mean, this definition is maybe not clear how it's functorial. So I say that the shape one can show refines to a functor pi infinity from topoi and in geometric morphism, so the right adjoints to pro of anima. So that's how the functoriality works. It's in the push forward direction. And the key example, which you can remove some hypotheses if you want, but let me say the easy one, is say you have T, which is a topological space admitting a CW structure. You really can weaken this a lot, but then in this case, actually this constant sheaf functor from anima to sheaves on T has a left adjoint given by the left con extension of the functor defined on open sets, open subsets of T, to anima, sending an open subset U to what I will write as bars U, which I mean the underlying homotopy type or underlying anima. So it turns out in this case, and basically you just need some local contractibility and say something about this hypercompleteness. Actually, this has a left adjoint. So what that tells you is that if you compute the shape of sheaves on T, well, I should apply this left adjoint to the terminal object, but the terminal object is the sheaf represented by T. And this tells me what to do. I should take the underlying anima of T. And I mean, this is kind of the input for this monodromy theorem that Clark mentioned in a talk whose number I don't remember. Yeah.
I think in Clark's talk, the statement was that if you look at locally constant sheaves and say a T like that, then this is a functor category out of the anima. And here are those two kind of related to each other. Here we're working with all sheaves.
Yeah, so what Jacob shows in the beginning of higher algebra is, so you can make sense of locally constant objects in any infinity topos. And I mean, you have to be slightly careful, but basically for locally constant objects to be a functor category, and that to be true local, like also locally, is equivalent to saying that you have this extra adjoint, and then it's always functors out of the shape.
I see. So there's actually a way to make sense of locally constant objects in any topos.
In any topos. Yeah, so you say anytime you have an effective epimorphism from a coproduct, or you can always find an effective epimorphism from a coproduct of objects so that when you pull back to these things, it becomes constant.
Precisely when the shape is an actual anima, then locally constant objects, that's a functor category.
Yeah, so you should say that the shape of every slice topos is an anima. So it could be the case that the shape is an anima, but then for some weird
Yes.
open, yeah, like, yeah. Okay. So the point here is that even though this definition is very abstract, what it tells you is, okay, in some reasonable situation, like for a reasonable topological space, this this abstract definition recovers something nice. But it makes sense now for any infinity topos. So, and I mean, this is basically what I'll say next is basically what was done in Artin and Mazur's book, though maybe not formulated exactly in this way. Is they say, okay, now I just input into this machine the étale topos, and then I get some answer. And maybe a priori you have no reason to know that that answer is reasonable, but then they showed it is. So the definition is that the étale homotopy type of a scheme X is pi infinity étale, which is the shape of this étale infinity topos. And so maybe to go on Peter's point, something I don't write down, but I'm of course happy to discuss after, is you can always show that locally constant sheaves with some finiteness condition are classified by this shape. And in general, locally constant sheaves without a finiteness condition won't be, unless you really have a genuine left adjoint. But using that fact, you can show that basically the pi1 of this up to profinite completion will recover the usual étale pi1. So, but it's understandable if you're very unhappy with this definition because, I mean, say, how can you possibly compute it? Well, I mean, you can't because in abelian geometry, I mean, we basically cannot compute étale pi1 except for some small list of examples. But anyway, let's ignore that. Let me try to instead now give you a different definition.
What if we start with something simple like the rationales? Can we do it then?
The rationals?
Yeah.
Well, I mean, if you win a giant bed of Fields medals for understanding the Galois group of Q bar over Q, then yeah. So okay. So what I want to do now is give you some more conceptual way of thinking about this. That somehow was also in the minds of Artin and Mazur who invented this, but yeah, they didn't have the language to formulate. But maybe I have to make one technical remark to do this. So there's a fact, which is that the inclusion of pro n less than infinity. So what does this mean? It's pro of truncated anima. So this means that the homotopy vanishes above some point. The inclusion of this into pro anima admits left adjoint that I call tau less than infinity that identifies this guy with something else. So it's some localization. And the weird thing about pro anima is that, well, if you know something is an equivalence after all truncations, which is not quite correct, but basically you should think of saying on all homotopy groups, it need not be an equivalence. So, but if you pass to this subcategory, it's the same as inverting those things. Um, and basically, no one in the world has ever said something about something interesting in here which was not already in here. Or yeah, so we just ignore this difference. And so yeah, we'll consider this protruncation of the shape. And an important fact is, yeah, if you're familiar with this world of hypercompletion, and you take the shape of the hypercompletion and you take the shape of the topos itself, then follows an equivalence after protruncation. That's basically saying any invariant you can compute about these things like the cohomology, it cannot tell the difference between these two things. Okay, so you got this maybe unsatisfactory, depending on your perspective, definition. Let me try to give you a more satisfactory definition from a different perspective, or at least a more conceptual one. Which is a theorem that's not so hard to show, but is very, I don't know, motivating for me, which is proposition. So this version of the étale homotopy type after you protruncate it. So that goes from schemes to the protruncation or protruncated anima. This is the unique hypercomplete proétale co-sheaf, whose restriction to what are called W contractible yeah, so I'll unpack what this means is the following. So yeah. So these W contractible affine schemes are some important class of schemes that appear in this work on the proétale topology. So how to think of them is analogous, or really a generalization of these extremely disconnected profinite sets that appeared in Clark's talk. So there are some schemes which in practice you cannot really write down explicitly, but for which all of these proétale covers are split. And so, yeah, for any QCQS scheme, you can look at the set of connected components. And that has a topology given by the quotient topology from the map from the scheme. And it turns out that that's always a profinite set. This W contractible affine condition guarantees that this is an extremely disconnected profinite set. And so profinite sets include into pro of these truncated anima. So it says that whatever this basis is, which, I don't really have time to say more about. So if you're familiar with the proétale topology, you know it. If you're not, just take it as some black box. Whatever this basis is, this is basically trivial. It's really producing just a profinite set. There's no interesting homotopy. But the magic is that there is lots of interesting homotopy for a random scheme. And it's just built from everything that lives on pi 0. And so this hypercomplete proétale co-sheaf, what does it mean? It means that if you find a hypercover of your scheme in this proétale topology, then you can write this invariant as a colimit in here of the terms in the hypercover. So that says that, yeah, up to this protruncation business, this guy can be written as a colimit for some simplicial diagram of pi knots of some hypercover by W contractible affine schemes, but where you compute this colimit in this larger category. And so that's kind of nice because it tells you some really nice universal property that is just the unique guy that satisfies this descent property and is something trivial on this basis.
What does pi zero mean?
Yeah, so it's the set of connected components, but now the set of connected components of a topological space actually has a topology, which is the quotient topology. Now, maybe you don't usually think of that, but when you start with a QCQS scheme, it turns out that quotient topology is always a profinite set. So it's really something rather simple. Yeah. Any other questions?
What kind of limits and or colimits does the shape functor preserve in general? Is there like
So it's a left adjoint functor from topoi and right adjoints to pro anima. So that tells you anytime, yeah, you have some covering in your topos, you can write the shape as a colimit over the covering. That's actually what gives you this property, the pro-étal cosheaf. The thing I wrote here tells you that it doesn't matter if I put the hypercomplete thing, and then that gives you this hypercomplete property. And then the uniqueness thing is just for some basis of Grothendieck topology stuff. And then you need to check one more thing, which is that this invariant on this type of scheme is just pi naught. But that's kind of
Is that why you need the hypercompleteness to restrict to the basis?
yes, because this basis doesn't even have finite products. And this is already a problem with extremely disconnected profinite sets. You cannot just take finite products of them. Okay, so now, why do I tell you this? Well, so I said at the beginning that I want some kind of condensed anima that has blah, 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 nice properties. Well, you can now stare at this definition and just change the target. So extremely disconnected profinite sets, they're condensed anima. Let's just change the target. And okay, it's not maybe obvious that that's a useful thing to do, but it turns out to be. So the definitions. So definition 1, which is maybe conceptually satisfying, but very hard to compute with. The condensed homotopy type so this I'll call pi infinity cond, going from schemes to now condensed anima. So is the unique hypercomplete pro-étal, yeah. I wish this were shorter. Cosheaf, whose restriction to these W contractibles is exactly as I wrote before. So I can take pi naught of one of these W contractible affine schemes. It's an extremely disconnected profinite set, and I can just think of that via the Yoneda embedding as a condensed anima. And there is a functor from here to here, but it's a right adjoint functor and it preserves basically no colimits. So the colimit you compute when you write this colimit, but it's in condensed anima, is now something else. But it's immediate that there's also a left adjoint to that functor that goes back to here. When you apply that left adjoint, you'll just get this by this uniqueness kind of property. So that's a perfectly valid definition, but how can you possibly compute anything? And that's where exotery comes in. So I was gonna say there's also some alternative shape theory definition, but I don't need it, so let me not say it. But you can do some analog of the shape theory business. How am I supposed to go here? You can do some analog of the shape theory business where you work over condensed anima and make exactly this type of definition. And it turns out if you did that for the pro-étal topos, this would recover the definition I just gave. But it's also not really computable. And then the magical thing is that, I mean, the definition that Clark and I proposed in this exotery paper agrees with this conceptual definition, but you can actually compute. So here's a definition via. So maybe I just remind you a little bit about what Clark said, or maybe I say a few things he didn't say. So say we have a QC-QS scheme. And I'll basically always assume this from now on. So with Clark and Saul, so we defined profinite one category, this gal X, such that the following things are true. So if you take the limit of this pro system, this gal X goes to something that's understood very classically already in SGA4, which is what's called the category of points of the étal topos. So it has some objects which are geometric points, and then the morphisms are specializations in the étal topology. And then the second key property is a relationship to the étal homotopy. So let me write B. I think Clark wrote this as N, but I write it as B, not because I love the notation, but because I'm used to it. For the left adjoint to the inclusion of anima into infinite categories. So this is just saying you invert all morphisms in your infinity category. So you can extend this to pro objects. So on your pro system of categories, you just apply this term-wise. And one of the results we showed is that this gal guy, it gets sent to the étal homotopy type. At least, yeah, up to this pro-truncation nonsense that you have to deal with. So then, thankfully for me, Clark has already told you maybe the first thing that this pro category actually you can regard as a condensed category, and wrote down a formula explicitly how to regard it as condensed category. So there's an embedding of profinite infinity categories into condensed infinity categories, and you could think of that there. And then you could also form the analog of this pro B there and ask what happens. So let me say, what do I do? Okay. So, uh, yeah, so let me write this B cond from so condensed infinity categories uh, to condensed anima for the left adjoint to the inclusion. And since this functor B preserves finite products, this is actually just given by composition with this. So it would send your condensed infinity category to the guy that sends an extremely disconnected profinite set S to B applied to the category of sections over S. So it's in some sense quite explicit if you can understand what your condensed infinity category is. And the theorem, which follows from a result of Sebastian Wolf, is if X is a QCQS scheme, then this pi infinity cond of X has another name, which is I regard this gal X as a condensed infinity category, and then I take this B cond. So still, you may be unsatisfied because these things are very abstract and you don't get a handle on them. And so what I want to do in the remaining minutes is try to tell you some results about this object and some computations. And these are basically all made possible because we can understand this and we can understand what this functor does to some extent. And I mean, somehow from the other definition look kind of impossible to do. But any questions before I?
I guess so this is a different, you're saying this is a different definition once we have this theorem.
Yeah. I mean, it's our original definition. but yes.
This is one of these weird cases where the stratified homotopy type is extremely simple. It's a one category.
Yes.
So, yeah.
Yes.
Almost like a triangulation.
Yeah, it's like because you take the limit over all stratifications, it becomes simple. Yeah. This is a very good point that Lucas mentions, is that this étale homotopy type is actually very complicated. Well, not saying that this isn't complicated, but it's one categorical, so in some sense you can describe it explicitly. And where the complication of the étale homotopy type comes in is inverting morphisms is complicated to describe. So maybe I quote David Nadler. He loves to say this thing that like humans are good at sub-objects, but we're bad at quotients. That's why in linear algebra, you always introduce like some orthogonal or some bilinear form, and then take the orthogonal complement and identify it with a quotient, right? Because it's easier for students because quotients are hard. Okay. Okay, but let me, stop chatting about this because I should actually state some results. And yeah, so it's a kind of long project, so I won't state nearly everything, but I just state some things to give you a flavor of, of, of this. So results. So maybe the first example I just want to mention is say for a field K, this object is not unfamiliar. And this is basically trivial from that perspective. The PyCon of spec K, it's one object condensed groupoid where the automorphism group is the absolute Galois group considered with its profinite topology. So that's just an easy example. Then there's the fundamental fiber sequence. So you may have seen this fundamental exact sequence for étal pi1, and this is the thing that refines it. So say we have f from x to say spec k. That's a QCQS scheme. And you choose a separable closure, k bar of k, then there's a naturally null sequence, which is you take pi cond of the geometric fiber that goes to pi cond of x, and then that goes to this BGK. This is a fiber sequence. So that gives you, under some conditions on pi 0, some short exact sequence relating pi 1 of this to pi 1 of this and the absolute Galois group. And the beauty of this is knowing the result about the étal homotopy type, Tim Holtschuh and Sebastian Wolf and I gave a very simple proof of the analog of that result. And the proof literally just works exactly the same because of this type of description. You use some category theory, which has nothing to do with algebraic geometry, and it's just kind of obvious. And we can do it here too, and it's very nice. So that's quite satisfying. Now, what I'm going to tell you about is what happens for some particular rings, and in which case we actually recover some new computations of the étal homotopy type that were not known before. At least I asked Eric Friedlander and Mark Boywan, and they told me they thought about either these things. Here's the theorem. So for a compact Hausdorff space, well, I can port this compact Hausdorff space into the world of algebraic geometry by looking at continuous functions from k to the complex numbers and take its spectrum. Now that's an enormous ring. What happens if I take the condensed homotopy type of it? Well, it's k, meaning the sheaf represented by k. So it's a condensed set. So this in particular tells you that this pi 0 cond, as schemes vary, even schemes over the complex numbers, you can reproduce every compact Hausdorff space. It's quite general. A corollary of this is that if you take this étal homotopy type of such a ring, and this was the thing that I think was very inaccessible, and it's a kind of nice, just immediate consequence. Well, the general you'll get is the shape of sheaves on K, at least up to this protruncation. So in particular, if your K admits a CW structure, this is just the underlying homotopy type. So that's also a nice way to recover underlying homotopy type of like compact Hausdorff spaces from algebraic geometry. Okay, maybe can I have a couple more minutes?
Sure.
Okay. Yeah.
Standard rules apply.
Yeah. Okay. So now I try to finish by stating, I think, 3 results quickly. So the first one is something you might not expect. And I think at some point it was quite alarming to us. And then, yeah, actually we got used to it. And yeah, so the theorem is, okay, you might say, what happens when you do A1 over the complex numbers? So Now, I'll say something even stronger. So I can take its underlying group, so the global sections of this condensed group, and then I can even take its abelianization, and this is not zero. So in particular, pi1 cond of A1 over the complex numbers is not the trivial group. And this seemed terrible. And how we compute this is using this kind of spider-like diagram that Clark described and this theorem. So, but the reason is because this guy classifies local systems with values in any condensed ring. And those things are quite general. So it's saying there's a non-trivial local system over A1 with values in a condensed ring. So, okay, that seemed bad.
Do you have a concrete example?
Yeah, I mean, you can take the group ring on the abelianization of this. And okay, it's not that concrete. It would be nice to say like, okay, if you take complex numbers with usual topology, that's not how we did it. Yeah, so let me state two theorems and finish. So the first one is some niceness result, and we prove a lot about this invariant. So say yeah, if X is topologically Noetherian and geometrically unibranch. So for example, smooth over a field, then what can you do? You can fix this guy up. So there's a quotient of condensed sets and also condensed groups that Clausen and Schulze introduced called the quasi-separated quotient. So it's some complicated thing. But the theorem is that that will recover pi1 étal. So it's some kind of version of a Hausdorff quotient in the world of condensed mathematics. And so you can do this mild quotient in this setting to recover étal pi1. We prove also a lot of formulas for this quasi-separated quotient in general. So that's one result. So the whole failure of this thing to be trivial lies in the fact that it's kind of non-Hausdorff in some sense. And then I state the final result, which is how does this compare to étal pi1 or pro étal pi1? Well, if you combine previous things I said, you would know for A1 over C, pro étal pi1 is trivial. So seems to be some problem. And so the theorem is that say X is topologically Noetherian, then what happens with this guy? Well, this pro étal pi1 has this special property that it's something called a new heat group. And you can do completion to any condensed group to get a new heat group. And when you do this, you get the pro étal pi1. But the problem is this doesn't classify local systems with coefficients in arbitrary condensed rings. This one does. Okay, I finished there.
When you say a local system on A1C, what kind of data is it specifically?
Yeah, so yeah, what you should say is so it's a pro étal sheaf on A1C. And then to say it's a local system slightly complicated. So what you should say is that there exists like a pro étal covered by W contractible affine schemes, so that when you pull back to these things, it comes from some natural comparison between like sorry, like the pro étal topos of this guy to
In this case, you meant like this would be some kind of sheaves on the pro étal side.
Yeah.
value than say condensed modules over a condensed ring, or
Or just sheaves on the pro side. So that kind of puts the condensed into it. You don't need to say. So you can always, there's a comparison between the pro-étal topos of any scheme and condensed anima. So you can always pull back a condensed ring and look at modules over that pullback. So
three are just say sheaves of abelian groups
on the pro-étal,
no compatibility between anything.
Yeah.
This kind of comes from the structure of the pro-étal
yeah,
side.
it comes from the structure of the pro-étal side.
This weird non-vanishing that you have there, which maybe you don't find it weird anymore. I still find it weird, I guess.
I mean, it's quite shocking, I think, right?
Is it, okay, so you say you've gotten used to it. You think it's a feature?
It's a feature in the sense
Or is it a necessity, I guess?
it's a necessity for sure. So yeah. So if you want this guy to classify all local systems, I mean, it has to be true. I mean, because you can write down a non-trivial local system. So if this is going to be trivial for A1, there's going to be a problem.
You restrict in the local systems that you're looking for, and
Yeah, so there's some natural questions you could ask. Like one is, can you refine whatever this quasi-separated quotient is to a functor on condensed anima and get some quasi-separated homotopy? The answer is actually no. It's actually impossible to do it having nice properties. For this Newhy completion thing, my memory, which maybe I can check with Katrin, is we tried to do it for a long time and we couldn't figure out how to do it. But we don't necessarily know that it's impossible, like for this thing. Is just that you write down some natural candidate of what this thing is, and it's not even clear that it's idempotent. And so for groups, it works by some, I don't know, easy kind of representation theoretic thing. But in general, it's not so clear. Yeah. So that's kind of weird. I mean, we tried quite a lot, and it seems maybe, but I think what Schulze said also is he kind of regrets even calling this a pro-étal fundamental group because he doesn't like this new completeness. If what I recall is correct, it's that yeah, I mean, it was useful for what they were doing, but somehow it has various deficiencies. One of them being it's kind of hard to say exactly like what types of topological rings you really classify local systems. So yeah.
So let's say I'm trying to get used to this like necessity of in A1, I don't get 0. And I want to think about like my fundamental group is telling me something about covering spaces. Is there some way that I can understand like some covering space perspective on this object?
Yes, I don't know if I have anything nice to say, but maybe I just make as some like advertisement or some kind of upshot is the other nice thing that we show in the paper, but it's kind of too long to talk about it in one talk, is that this pi1 cond US is nicely behaved. And that we can actually analyze it. We prove like a Van Kempen formula, a Kunith theorem. You can easily prove a short exact sequence for this quasi-separated quotient, where like Martin Lara proved this type of thing for pro-étal pi1 in his thesis, and it's super, super difficult, actually. And the other kind of amazing thing is that under some pretty mild assumptions, this thing is actually a topological group. But it's just better in many ways than this guy. So, and in particular for A1, it's tricky. So, it kind of behaves more like you would like. Yeah.
Maybe let's thank Peter again, and you can ask him questions after.